Okay, what we're going to talk about today is, for the most part, physics. And in the previous session, we talked about mathematics. So I'm going to try to do physics, maybe we could say, with a minimum of mathematics. Okay, and I'm going to sort of start and review a little bit the basic premises. And what I'm going to say is that if we look at, let's say, existence, there are really only three types of stuff that comprise existence, or our internal and external environments. And the first one of these is physical, and it's mechanical. And what I'm going to suggest it is it's energy stuff. And so what it is, since it's physical mechanical, it's sort of physical energy stuff. And this is really is what pure physics deals with. But in order for this to have relevance to our day-to-day lives and so forth, this has to be processed by, for us, a human neural entity. And again, as we did, what I'm going to do is I'm just going to focus on the highest level of that, which would be the human brain, which then perceives or has perception of the physical through our sensations, and it can process it, and very importantly, it provides a representation of it. So what we have here is we have physical mechanical energy stuff, and then we have human neural processing or brain stuff, and then these two are intimately intertwined. Now, the energy stuff is sometimes called nature or nature's way, and its laws are often referred to as absolute. But what you have to realize is that these laws are actually representations of this that come from the neural stuff. And we could call it neural energy stuff, but we got to realize it's a different form of energy. Okay, it's neural energy stuff, whereas this would be physical energy stuff. And the correlation between these two forms another reality. Now, I could put a box here, and I could put a box here, and I could say, okay, put a check mark in whichever one of these you want to be absolute. And what a physicist would do, since they deal mostly with physical mechanical things, would say the absolute reality, and this is what Einstein did, was the nature's physical existence. And what a humanist would do is he would say, so he would label this number 1, and let's say this number 2. What a humanist would do is a humanist would check this box and say the only real reality is that which has been processed by the human brain. Therefore, this is the operational reality that we have to deal with on a day-to-day basis. And while the physicists would call this absolute, and there'd be probably some difference between our ability to process it and describe it accurately, what a humanist does is he says, well, we don't really have to worry about this. What we'll do is we'll just look at the combination of these two things, and then we'll see if we can operate and apply things to get results that we can, with the previous intention, control, so we can control the results and predict the results. And that's probably a pretty good definition of a scientific approach. And what people that are that approach this, let's say through the humanities, they don't say the physical doesn't count, because actually, the brain is composed of things that have to operate according to these laws. But what they say is we'll put them together. Therefore, you don't just do this. And what really matters in your day-to-day life is the reality of how these two interact. And the real reality isn't necessarily that it exactly describes this, but you put the scientific method in here, and you actually develop a system where, with understanding, which is part of the design of the science, which enables you to set up the system that you're going to control and predict, you then you can operate it, you can apply it, and you can get results that you intend and control, which is probably a good working definition of performance. So, if we take a look at how humankind is kind of operating all of this, okay? This kind of describes the way it works, and it gives you a definition of physical existence. It gives you a definition of the neural processing of the physical existence. And then, in terms of if you operate it in this way, you get a definition of reality, which involves both understanding and operation through, basically, and I'll just, I guess I'll write it here, a process that we could call science, or the scientific method. Now, there's a third component that, since we're talking about physics, we won't go into in great detail. But the third component over here would be spiritual or faith. And these are things that we can kind of feel, and we can feel that they change things and so on and so forth. But it can be very difficult to connect them directly to physical things. And this connection here, okay, now moves more towards humanities as a science, and let's say feelings, emotions, and religion as a faith or a spirituality. And, you know, just to give it a name or something that, you know, we can hang our hat on, is we can say that if you're dealing with human beings, not plants, and let's just, I don't want to get into controversial areas of this, but, you know, lower level animals and so forth, we're dealing with things that involve the fact that humankind has a soul. And in fact, you know, with the older philosophers and stuff, they actually, you know, put that in the human brain. And, you know, there was a statement that the pineal gland was thought to be the physical location of the brain that connected with spirit and faith and the soul of a man. Well, with this kind of setup, what I'd like to do is I'd like to historically track how physics and our understanding of the physical world as represented by humankind has evolved. And I'm going to represent these two things as, or the physical part, is something I'm going to call energy stuff. And what that means is we can represent it as energy, but it's not just energy. And you know, the famous equation E equals mc squared, or if you don't go to mc squared, that energy, and just do it this way, energy is equal to mass times velocity squared, which is then mass times change in distance or space squared over time squared. And the other one that describes another form of energy, which is actually light or electromagnetic radiation, and the expression of that is, and again, this is more advanced than we need to go into, but I just want to show that energy stuff can be processed by the, and I'm going to call this human neural stuff, which includes physical energy stuff, but actually doesn't have to obey all these rules and everything. So what we have is we have this, okay, which is a representation of this, and then we have this, which is absolute in terms of if we're dealing with physical things, and not just human neural things. And we want to look to see how well they match up, because that really kind of defines the reality of that interaction. Now, if I track this historically, what I'm going to try to do is I'm going to try to explain a little bit what the physical energy stuff is. And in order to be classified as physical energy stuff, we have to be able to perceive something, and for the most part, we have to be able to measure it. And one of the things we can look at, and we talked about this in terms of mathematics, and the number one kind of connotes how many and how much, is let's just say that at this end it's big, and at this end it's small. And let's talk about the biggest thing that we measure or feel that we know it physically exists. And what I'm going to suggest is that that is the universe. And the universe, talk about a big number, is 13.8 billion light years. That's its dimension. And again, without going into the geometry of it and some of the other things we talked about in terms of mathematics, okay, and then we don't know for sure if there isn't something even bigger than that, which we could represent as infinity. But let's just say now that humankind's brain is processing now something that's 13.8 billion light years in size and quantity. Now, what I'm going to suggest is, and I'm going to go back here a little bit to existence, is since we can measure it and we think we have physical evidence for it that we can process, we would say that's existence, that the universe exists. But we don't really know how far it goes, so there is then the possibility of non-existence. And if we define non-existence as that which we can't measure and we can't imagine or process neurally, then we have a definition for non-existence. And then we also have another category that we could logically include, which would be possible existence. So now if we go back to what we're really trying to establish here in terms of neuroprocessing reality and so forth, we're going to deal with basically the totality of existence, which would include existence, non-existence, and possible existence. And what I'm going to try to do is I'm going to try to sort of track historically the neural processing of nature and physical existence by humankind. And I guess what I should probably do is introduce here is that if this is the biggest, there's something down here, okay, that's the smallest. And the smallest thing that we can perceive down here is called a Planck unit. And there's the Planck, and the Planck unit is, and I think I've got this right, it's such a small thing, if I'm off a little bit, it's 10 to the minus 43rd meters. Now, what I'd like you to understand that I'm trying to represent here is I'm trying to represent the biggest thing that we acknowledge it exists and the smallest thing that we acknowledge it exists. Now that doesn't mean, and now we're on this side now, instead of infinity, we're processing 1 over infinity. And then these things may go to, I'm going to call it 0, but that thing that we would call a singularity. But in terms of what we're doing on a day-to-day basis and what we've actually got to work with in terms of reality, we can understand a universe and we have a dimension or a measurement of it, and then we can also understand and we have a dimension of the Planck unit. And given those definitions or those operational things, it would seem like we could get clues in terms of being able to, using science, to operate, apply, and get results that we intend and control to get performance. But let's take an historical perspective to this. And what I'm going to try to do here is I'm going to say that we now know more about the universe than we used to. It's bigger. Okay? But let's go back to approximately, and I'm going to call this year 0, so it's not BC or AD, and then a little bit 0 to 500 years before 0, or BC, and I'm going to put in here the Greeks, because they were the first ones that are given credit for, because they recorded it, trying to figure out what was actually going on, and asked the key understanding question of why. And, you know, we're talking about Socrates, Aristotle, Plato. I'm just kind of grouping it together. But they asked the question, why? And they developed kind of an operational thing in that what they couldn't understand, they created gods for. But from a scientific standpoint, what they couldn't understand is they created entities that interacted in a certain way. And I hope I can get it. Earth, water, wind, and fire. And they said they all sought their place and so forth. So this was sort of the very primitive scientific method of asking why, and then trying to build a model where they could explain how things worked and operated. Well, without getting into a lot of detail about what actually caused the Dark Ages and so forth, this kind of rubbed some people the wrong way and so forth. And we're going to jump ahead now, and again, this isn't drawn to scale, to the year about 1500 AD. And the person I'm going to put in here is, this is the Dark Ages, the person I'm going to put in here is Galileo. And what Galileo did was, he sort of came up with, okay, this idea and refined what the Greeks were doing of science and the scientific method and so forth, where you would ask a question and then you actually had a way to set up and understand the question you asked, and then have an idea and do some measurements and so forth, and come to some type of better understanding or better way to operate things. And this was a major breakthrough. And in addition to this, and his stuff was mostly, I would say, in the physical sciences. But one of the things you note, if you go back and you track this, is when things were still fairly big, and we're dealing with larger physical things, almost all the people who did physical stuff also did philosophy. And in our previous talk, I mentioned that when you look at people like Descartes and people, you know, that are just giants in these areas, that they almost all did not only physics and philosophy, but they did math, because when you get to this level, it's pretty easy to see that these things are really kind of all part of the same thing. And when I say to this, or you operate at this level, I mean things are fairly large, and you're just looking for clues anywhere you can get them. Well, what happened was then, in about, I don't know, the mid-1700s, a man came along, his name was Isaac Newton. And what he did was, and you know, he was able to collect some things that were smaller, but what he really did is that he created, I think it would be fair to say, a way to deal with, he used Galileo's science, okay, and he dealt with the physical, mechanical stuff. In other words, this. And I want to talk a little bit about what he did, because it can kind of be grouped into two parts. And I think going through it this way is a good way to understand some things that can become a bit misunderstood or overly complicated when you look at physics and fairly basic physics. The first thing he did was he established, and again, this is all, he did a lot of other things, let me just put it that way, the laws of motion. And one is, the first law is the law of inertia, which basically says that things at rest tend to stay at rest, and things that, and then he basically defined energy, and he did this kind of by rolling balls down inclined planes and applying some mathematics and so forth, and he came up with force equals mass times acceleration. And then the last thing he did was another one of these laws of, in terms of physical things interacting, was what you can call action and reaction. And those three laws are basically, things at rest tend to stay at rest. You can quantitate the interactions, and then for every action, there's an equal and opposite reaction. And those are the laws of motion. And those laws, okay, for the most part, okay, are just physical laws. The other thing that he did, and this is all Newton now, is he looked at gravitation. And he came up with the laws of gravitation. And basically, this is a law of how a force operates. And it describes how things will change in a certain defined, and I'm going to call it a domain. And what he said is that a force is equal to mass 1 times mass 2 divided by the distance between the two masses squared. Now, that was really good because he now had a relationship between two masses, or two things that were matter, and it enabled you to predict where things were going to go, or visualize it more easily if you considered it to be a field. And he called this mysterious thing between these two balls a field. But he was actually a very precise and intelligent guy. And he knew that he was fudging it, because he was describing something that, although he could describe it and make measurements on the things that had mass, he had no idea what was there. And he really didn't think there was something not there that would cause things to change. He was smart enough to know that he just wasn't smart enough to know what it was yet. But what he developed to deal with this, and a big part of it is something we went over last time, and that is calculus. And calculus was a way for him to have a representation of, and it's a mathematical representation, of things that happen without actually knowing exactly what's going on. And so he called that a field. And again, let me say that then what a field actually is a mathematical representation of the way things are going to happen, even if you don't exactly know what's going on or why they're happening. All right, so that's Newton. Well, the next guy who came along, oh, and let me say, in terms of the mathematics of the field, there's controversy in terms of who actually invented calculus. There's a man who was more of a pure mathematician named Leibniz, who sort of described calculus at the same time Newton did. And maybe because Newton gets more traction because he was doing it and related it to gravity, you hear more about Newton inventing calculus than you do Leibniz, but I want to give him his due. But now Maxwell comes along. And what Maxwell did was he looked at not gravity, but he looked at a thing called electromagnetism. And the observation is that when a charge moves, and it's interesting, a man named Oersted was just giving a talk and he ran a current through, and behind him, okay, he had a magnet, you know, thing that would measure magnetic field, and every time he turned it on, it moved. So he basically just kind of stumbled onto this. But what Maxwell did was he developed 4 equations that are still solid gold and taught in engineering and everything else that described the relationship between the current flowing, and let's just say that's a negative charge flowing that way, and this magnetic field that's going around it. Now, the similarity between what Newton did and created a field and what Maxwell did was there's a physical observation. Okay? In other words, this current flows and then there's something that moves, and it moves because of the electric current and the magnetic relationship of the thing that it's changing. But if you look at the two of them, for example, if I take, and I'll just draw this very roughly, if I take, okay, a piece of paper and put iron filings on it, and then I have a magnet here, those iron filings will line up in a certain way. So there's something going on between the magnet and the iron filings. Just like over here, there's something going on between the two masses, but we can't see it. So what we call what's between the magnet and the piece of paper with the iron filings on it is a field. And then what Maxwell did was he wrote equations called field equations that mathematically described how this field operated, just like Newton had written equations to show how the gravitational field operated. And lo and behold, if you look at electromagnetic fields, let me see where I've got this here. Oh yeah, okay. I've got it here, so I'll just put this one here. Instead of mass interacting with mass, what you do is you have a force of charge, which is equal to one charge times another charge, divided by the distance between them. And then you have a force of magnetism, magnetic force. And what that is that's one magnetic pole times another magnetic pole divided by the distance between them. Now, his four equations are more complicated than this because charges and magnetic poles aren't exactly the same and so forth. But what you see is that this, that Newton did to describe a field, and this, which Maxwell did to describe a field, both have a similar relationship, and that is, these are called the inverse square laws, where you take the two things and you divide them by the distance between them squared, and you get a representation of the force. Well, without getting into much that's a lot more complicated than this, the next guy who kind of came along and did something that was monumental was Einstein. And what he did in simplest terms is he took Newton, and Newton's stuff is called classical mechanics. And he combined it, okay, with Maxwell's work, which basically, when Maxwell did his work, what he found was that another form of energy is light or electromagnetic radiation. And Einstein basically took and used what was known about gravity and electromagnetic radiation to come up with, first of all, his special theory of relativity. Which described the way things worked in classical mechanics when it was combined with Maxwell's field equations. And Maxwell's field equations actually, when he did them, and he combined the electric field and the magnetic field, he came out with waves that traveled at the speed of light. And this is a real example of he came up with something before he could see it. But what he realized was, since it traveled at the speed of light, that it must exist, okay, although we couldn't detect it. Now, unfortunately, and this may be why he didn't get his due, Maxwell's mother died at about the age of, I don't know, 40 or 45 of cancer. And he died relatively young at about the age of 50 of cancer. In fact, he never got to see the physical experimental proof of the fact that radio waves and gamma waves and everything else were the same as light, except that we couldn't see them. But the guy who did that was Hertz, and that's a different story. But he actually demonstrated radio waves. Now, what we've got now is we're sitting here and we've got Newton, Maxwell, and Einstein, and we've kind of progressed, and Einstein has put these things together, and he then worked out the special theory of relativity, which didn't just deal with the laws of classical mechanics, but he realized that he needed to deal with the gravitational field. So then he created general relativity. So now we're sitting here and we've got something that actually puts gravity, what's at that time known, gravity and electromagnetism together in this theory of general relativity. And one of the most amazing things about Einstein is when he did special relativity, they didn't even know there were molecules. They didn't know there were nuclei. There didn't, which shows how solid his reasoning was. And it wasn't. I mean, there was mathematics involved, but it wasn't really complicated mathematics. It involved, and again, this is things like the Lorentz transformation with special relativity, and then Gaussian coordinates and difference between straight lines and curves and stuff we don't really need to go into now. But now what happens is we start to be able to process things now that exist physically that are much smaller. And what that's called is quantum, and there are reasons for this. But the basic unit of quantum that's measurable and you can manipulate is a Planck unit. And it relates to frequency of radiation. And radiation is really energy stuff that doesn't have mass. Okay? But this makes the point that not all energy stuff is, and I think I put this up here, isn't E equals mc squared or v squared. And that when you move over into the domain of massless energy, as things get smaller, you have to process it differently, and the rules change. And what happened was that the people that took this and developed quantum mechanics were sort of in the same bind that Newton was in. That is, they knew how things worked, okay? But the exact mechanism of how they worked, they really didn't know. Just like Newton had created a gravitational field, and he could write all these operational equations, but he didn't really know how it worked and what it was. Einstein figured this out for gravitation. And we can talk about, because that's the general theory of relativity, which kind of puts it all together. But as these people got into smaller and smaller things, they ended up where they needed to operate it, but they still didn't really know how it worked, because Einstein had actually figured out the basis of how gravity works, and I'm going to explain to you how he did that. But they really couldn't figure out the way that electromagnetism worked and electromagnetic radiation. They could write equations for it, but they didn't really understand exactly how it worked. Now, what I'm going to do next is I'm going to, in terms of the historical example, is I'm going to give you an idea of how Einstein figured this out, and then how what he figured out in terms of general relativity was validated. And then after I show you that, I'm going to explain to you that today, and I'm not going to list them all here, one of the big problems is, and this is acknowledged at the highest level of science, is that they can't unite gravity and electromagnetism, and they can't unite the general theory of relativity and quantum mechanics. And as they look at the spectrum of the physical things that exist, okay, and we could kind of say that the Greeks and everybody to here and then on, for the most part, further on down, okay, what they dealt with was the planet Earth, and you can call that terrestrial, and a term that's not often used, but humanos has to do with where human beings are. Out here, where things get bigger and beyond the Earth, this is called the cosmos. And that's called cosmology. And then when things get really small and they're still inside the Earth, this is called the quantum world. And that's described as quantum mechanics. And what we're basically saying here is that in this part of the world here, which operates, and let's say for the most part in the universe, not all of it, we've got a pretty good idea what's going on here. But when we get down to where things are very small and we start dealing in Planck units and everything, that we can't put gravity and electromagnetism together. We can't put general theory of relativity and quantum mechanics together. I'm going to suggest that we don't really know what charge is in the context of the way Einstein described it. We have controversy in terms of what the model for this whole thing is. And what the quantum people have said is that the whole model is different. And what Einstein said was, it doesn't make sense that the basic model is different. You guys are just sort of fudging things the way Newton did to explain his fields, and they can't write those field equations. And we're going to call this the standard model here. And they've introduced things like the uncertainty principle and the idea that there is no real physical energy stuff, that actually once the brain gets involved, it's all statistics and probability. And this then is a big divide between Einstein and quantum mechanics. And when I show you how Einstein got to where he got to, I'm going to try to explain why I think that the methods he used and how he got to things would be preferable, not necessarily to operate things, just like with Newton, but to actually understand what's going on, which then would set the groundwork for going further in terms of science and what we can operate. The next thing I want to do is I want to show you exactly how Einstein, So the next thing I'm going to do is show you exactly how Einstein solved the problem with gravity with the general theory of relativity. And then I'm going to suggest to you that if you apply the same methods to electromagnetism, you can solve electromagnetism with whatever we're going to call that, and then you can actually put them together. Now, in order to do that, I'm going to have to create a little bit more space here, and I think where I'm going to put it in is going to be here. And what I'm going to take out is, since this is all sort of the same, and this is a definition of science, and this is sort of the overview of everything, what I'm going to do is I'm going to then describe Einstein's version of energy stuff and how he looked at it in terms of the human brain, and used some mathematics, but didn't say that it all had to be mathematically equivalent, because he figured it out with words and logic, mostly. And that kind of comes back to, and I can add this up here, that if we look at the physical energy stuff and the neural energy stuff and its representation, there are sort of three ways we can connect these. We can connect them with words, we can connect them with symbols or numbers, which we talked about when we went over mathematics, and we can connect them with images. And I'll probably refer back to that a little bit as I go through what Einstein actually did. What I'm not going to do is go into a lot of detail about relativity. What I'm going to try to show is what relativity led to in terms of Newton and Maxwell, and give you an idea how, if you use the same approach, you can put gravity and electromagnetism together and get an idea of how it all works the same, and maybe even give you a little bit of an idea of why I think it's so hard to do, and a different way to look at it that might make it easier. But what Einstein did was he came up with this famous equation that energy, or energy stuff, is equal to mass times the speed of light squared if you're in a vacuum on planet Earth, because c is equal to the velocity of light in a vacuum. It's very important to include in a vacuum, because if you look at energy, okay, what I'm going to suggest is that energy has certain characteristics that you have to. One is it has a boundary, or it has to be considered to have a boundary. And in that case, then, you can deal with it as an entity or entities. And when you do that, what you can say, and is proven by science and experience, is that inside a boundary, energy is neither created or destroyed. And with our initial reference to mathematics, we can express this mathematically by saying that within boundaries, energy is equal to a constant. And what I'm going to suggest is that it's a function then of mass, space, and time. And it can't be equal to zero. That is to say, if you have no mass, no space, and no time, you don't have energy. And if you don't have energy, since I'm going to define energy as the presence, I'm going to define existence as the presence of energy stuff, then you don't have anything. So, if we start out with Einstein and we say that energy equals mass times velocity squared, or which goes to the speed of light squared, what we sort of end up with is, we end up with this, where what's happening is, in a closed system, as the mass decreases, so things get very, very small, okay, the velocity or the relationship between change in space and change in time, okay, it gets very big. Because as this gets bigger or smaller, this has to get bigger. And there's a reason why time is in the denominator and so forth, that it's inversely proportional. And this is really kind of what, if you go through relativity, why things shrink when they go faster and so forth. But what really comes out of this is that mass, space, and time physically are compositional. And what do I mean by that? What I mean by that is that if you look at physical energy stuff of nature, okay, it actually is composed of mass, space, and time. And you can mix them in different ways, just like you can mix different colors in a liquid or something. And what I'm going to suggest to you is that if you have all three of them, you have matter. If you have just mass, what you have is the equivalent of a black hole. If you have just space, you have a vacuum. And if you have just time, I'm just going to call it, you have eternity. And what Maxwell showed was that if you have just space and time, what you have is light, if we can see it, or electromagnetic radiation. And the equation changes from E equals mc squared, or E equals mass times space squared over time squared. And then as mass goes to zero, space squared over time squared becomes the speed of light. But once it becomes the speed of light now, it's radiation because there's no mass. And when it gets over here, it becomes a relationship of a constant times a frequency. But how did Einstein actually take this forward? Well, what he showed was that gravity really was mass, or let's just say mass for now, warping a membrane that was composed of space and maybe time. That can be a little controversial. So what he did was he actually separated matter into mass and allowed it to interact with space and time, or with space. And how did he, and he shows this eloquently, but then given the fact that we didn't have all these things that we have now, what experimental evidence did he marshal for? Because, you know, you can't, by science, you can't validate a theory unless you can run an experiment that verifies your theory. Well, there were three things that could not be explained except if you took this model, which is basically relies on the general theory of relativity. And when you used the general theory of relativity and the mathematics that followed, you could explain the motion of the perihelion of Mercury. And I'm going to explain that in simple terms. You could explain, let me make sure I get this right now. You could explain the, I'm blanking here just a minute, the perihelion of Mercury. You could explain that, and he postulated in that the deflection of light by mass, which is basically if space and time are light, a mass then should deflect space and time as it distorts that membrane, which is what light is. And the last thing was you could explain the red shift of spectral lines in space compared to terrestrially or on Earth. Now, these may be, and I haven't written those very clearly, but these may be a little bit more advanced. So it's more the concept that I want to go into. And remember, he had to do this with fairly big things. And this actually helps you kind of understand the difference between cosmology and this, and then quantum, which is somewhat different. If you look at Mercury and how it moves around the sun, it doesn't move in exactly the right ellipse that you would predict if you use Newton's laws of gravity and classical mechanics. It rotates. Now, actually, all the planets aren't perfect ellipses. But since Mercury, okay, is closest to the sun, and the sun is this gigantic mass, okay, it's the only planet where even now we can measure it properly. I think even now, those things are changing every day, where you could see this rotation. But there was no other way to explain this rotation with classical mechanics or special relativity other than this explanation of the gravitational field, which isn't a bunch of equations that Newton wrote to say how it operated, but it's that the actual mechanism is mass warping space and time, and then the field equations that followed are the general theory of relativity equations. The second thing, besides the perihelion of Mercury, okay, is the deflection of light when it goes by the sun. And this was the thing that really put Einstein on the map. And he couldn't catch it the first time because of the First World War. You had to get in the right place on Earth. But what it showed is that if you take light that's coming, let's say, from a star here, and it's coming at this angle, when there's an eclipse, you can see the light and it bends. And the only explanation, okay, for light, that's not two masses, okay? The only explanation for that is that when this light, which acts like a membrane, gets close enough to the mass of the sun, it bends. And then that's the general theory of relativity, and then you can write equations that'll show that. And the last thing is this redshift in the spectral lines, which showed that if you look at things in outer space, that the frequency of the light, which is what you're observing, changes to a lower frequency. And that's called a redshift. And that's caused by the fact that since the universe's mass, if it's moving away from you, it's going to change the relationship of the light. And you don't get this redshift on Earth because on Earth you don't have the stuff of the universe expanding. Now, an interesting thing about this, and we're not going to go into the Big Bang, but if you look at the Big Bang, where things are supposedly here, what they say is that, you know, and I can't give you the exact numbers, that in the first 2 seconds, the size of the universe was, and these are round numbers, let's just say 100 light years. So you say, well, how can that be if nothing can go faster than the speed of light? Well, that's why you have to understand that the speed of light is in vacuum. It's on Earth. Okay, which isn't even necessarily in vacuum, but it's, there's no great density. So that what's happening is the stuff of the universe and the amount of energy is expanding to the point that you not only have to take the speed of light, but you have to take the speed of the velocity of the expansion of the universe. Okay? And then it can go faster than the speed of light, because it's the speed of light plus the expansion of the universe. So it's one energy plus another energy, and that's what causes this shift. And what I'm going to suggest to you is that the equations that will explain that are the equations of the general theory of relativity. So it's not easy to do, but basically what Einstein did was he looked and he established a relationship between energy, mass, space, and time, and then he described actually how that worked and enabled equations to be written, which were basically field equations that described 3 things that had been observed. Now, as we've gone down and things have gotten smaller and smaller, like for example, we don't use a mechanical clock anymore, we use a cesium clock, which is a molecular vibration and so forth. All of the things that he's put into, or that he came up with in terms of how it actually worked, in terms of general relativity, have proved to be exactly accurate. And the equations that came out of the general theory of relativity have been shown to be completely accurate, except, okay, when you get down here where electromagnetism and so forth are more operant. And what's happened is, as these things have gotten more operant, these quantum people have said that as things get smaller, the way Einstein looked at things, progressing from classical mechanics to Maxwell to special relativity to general relativity, just don't hold anymore, because they can't write the equations that explain both sides of this. They can write equations that explain the electromagnetic side physically, or in terms of a field. And Einstein, of course, with this line of reasoning, was able to write equations that describe the field equations of gravity. In fact, what he did was the solution to the problem of gravitation by the general theory of relativity. And it's validated not only by the experience and the observations, but it's also validated that equations have been written. On this side, they have written equations that will enable you to manipulate and build plasma TVs and everything down in this very small world. But what they've kind of said is these aren't equations that involve the physical world, they're actually just statistical and probabilistic equations. Therefore, there's no reality in the quantum world. Now, interestingly, the two people that objected to that most vigorously were Einstein, who'd already done it in this other area, and that was his famous saying, God wouldn't play dice with the world. And the guy who took, and I'm just going to say this, took the matrix mechanics of Heisenberg and expressed the same thing. I don't know if he took it, but who expressed that reality in terms of an equation called Schrodinger's equation, which is the basis, for the most part, for all of quantum mechanics. And interestingly enough, besides Einstein, he's the other guy that said, no, that's not what my equation meant. But because they can operate all of this stuff, they've proceeded with it. But they're things that they can't fit together. And their hope is that they will do more and more measurements and experiments in this quantum world that will enable them to fit both of these together. And my premise is because they haven't used the same approach that Einstein used to develop general theory of relativity, which explained gravity, they're not going to be able to find an explanation for quantum mechanics that's going to fit with gravity. And that's sort of the next thing that I'd like to proceed with in terms of where physics is now, what about it is problematic in terms of understanding it. Side with Einstein in terms of, and there'll be 8 of them, things that I'm going to lay out, but this is kind of the background, and actually show how I think they can be done with the simple understanding of science, which I'm not accusing the quantum mechanics people of not understanding, but the relationship between the classical mechanics of Newton and what Maxwell did and how Einstein put them together. And if you do it the same way, and I think have a little different understanding of what mathematics is, especially calculus, you can fit the whole thing together and get a solution.